All right, so today we're going to talk about frequency, period, and oscillators. We're going to talk about harmonic oscillations. Harmonic just means that, and oscillations means that something that repeats. It's a pattern that repeats, okay? So that's what we're going to focus on today. So you don't need to write these down. You're going to write them down in the notes anyways, but look for these terms. One is frequency, which some of you guys probably already know. The other is period, which some of you guys may already know. The other is amplitude that you may know. And then oscillator. Now, oscillator just means something that goes, it has a pattern that repeats. So you can think of a spring, right, with a heavy weight on it. If I drop the weight, it'll bounce down, then the spring pulls it back up, and then gravity and the spring will bounce like this. A pendulum that swings back and forth, same thing. Gravity pulls it in. It has momentum. It goes, swings back up, swings back around. There's other ones too. We'll talk about those today. This is what I need you to write down. So the period of an oscillator is the time to complete one cycle. And so just for clarification purposes, this right here is period and the F is frequency. So the capital T is the time of the period. I'm trying to get this. There we go. I don't know why it does that when I first start using this. So this is the time, capital T time of period. And basically how much time it takes to complete one cycle. And then F is just the frequency. So that's a mathematical relationship between the time it takes to complete a cycle. So if I wanted to know the frequency of a pendulum, I raise the pendulum over here, hit a stopwatch, let go, time how long it takes to get back to its original position. Whatever that time is, that's the period it takes to complete one cycle. Now, if I take the reciprocal of that, that gives me the frequency. And vice versa. If somebody tells me the frequency, then I can figure out what the time is because they're reciprocals of each other. Now, this deals with waves. Waves are sinusogenous, which is a fancy word that just means it's a wave. So you could talk about light waves. You could talk about electromagnetic waves. You could talk about motion as waves, like the pendulum and a weight on a spring being a wave. There's lots of things that repeat. Your heartbeat repeats on a cycle. There's a little bit of time in between each beat, right? And so it's a kind of an important thing that your cell phones, 5G stands for 5 gigahertz, which is like 5 billion cycles per second. And that's like a cycle of transmitting data going back and forth. Well, it's actually, it has more to do with the wave. But that's why 5G is faster than 3G, because it has 2 billion more cycles per second. Anyways, does everybody have this written down? So how does motion of a pendulum, how is the motion of the pendulum different than the motion of a falling body? Well, there's some similarities for sure, right? When my pendulum is right here, it's kind of like a max height. So you want to sketch all this out. Just sketch the pendulum and what I write down. Okay. What else is similar to a free fall? Well, G still acts on it, right? The acceleration due to gravity pulls it down at 9.8 meters per second squared. So as that pulls that down, it sets this thing in motion and it swings this way. This is the minimum height. Momentum keeps it going, right? Remember that the momentum is the mass times the velocity. Over here on this side, gravity's pulling it down again. So it reaches another max height when it gets to this side. So in free fall, we shoot something up in the air, gravity pulls it down, and it comes back down. Starts in one place, goes to a max, and comes back down. On a pendulum, you start at the max, come down, gravity pulls you back up to the max. That's because of the tension in the cable, right? But what happens if I were to measure this distance? This would be a negative, this distance right here would be a negative x value. Let's assume that this is x equals 0. And then over here, this would be a positive x value. And so the x values are going to be positive to negative, negative to positive. And this is all going to happen over time. So one trip I got to move my face. One trip. I probably should turn that off. I don't think anybody ever watches that anyways. One trip. So if I start here, turn around and come back, that's one cycle. And the time it takes is t, which gives me a frequency if I do the inverse of it. Okay? So if I have a stopwatch and I measure the time that takes, that's my stopwatch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I'm off by 1. 12. I was wondering why the 1 was weird. Let me make it a little better. So this has to be 12. This has to be 1. This has to be 2. So if I put a little stopwatch on there and I check to see what the time is, whatever that time is for one cycle, and it's going to be in seconds. Because everything we do is in seconds. So what would you need to measure and describe it exactly? Well, you can measure the position over time. Okay? Does everybody have everything that I've written down on your paper? All right. So let's look at it like this, a little more accurately with numbers. The pendulum swings back and forth. The motion repeats itself over and over again. Those are called cycles. Whoops. And then if I graph the position over time, it looks like this. I do want you to kind of sketch that graph. So what they're saying is that this ball swings all the way over here to 10 at some point in time. And then at another point in time, it swings all the way over here to negative 10. And so they measure that. It starts at negative 10 at 0 seconds, and then it crosses right here, and then it goes all the way to positive 10, and then it crosses right here. So what we're looking for, if I wanted to know the period, it looks like the period is 7 seconds. So the time, and how did I figure that out? Well, I started here, right? I started down here, and I went up and came back. And then right here is 7 seconds. So the total time, or the period, is 7 seconds. Now the frequency is the reciprocal of that. So 7 is the same as 7 over 1. So the frequency would be the reciprocal 1 over 7. This is 7 seconds, and this is 1 over 7 seconds. Okay? And there's a little more to this, which I'll show you later, because you can figure out hertz and all that stuff. We'll dive in deep on that. Now, the other thing I want to point out is the amplitude. So one of the terms that we talked about earlier, was amplitude. So the amplitude is how high it goes up and how low it comes down. So here I'm moving 10 units. Here I'm moving 10 units, but in the negative direction. So we would say the amplitude equals 10. And sometimes we would say negative 10 because it starts as a negative 10. It just depends on the application. Okay, is there any questions so far? All right, do you guys have this written down, or do you need a second? Can I move on to the next slide? Okay, I'll wait. Today's physics lesson is brought to you by Fairlife. Lastly, I probably should mention that one full cycle, this is one full cycle. So let me change the color here to like yellow or orange. So if I start here, this whole box from beginning to end is one cycle. You finish where you start. So if I started way down here at the bottom at negative 10, the next time I hit negative 10, that ends the cycle. Okay. All right, can I move on now? All right. So write this down. An oscillator is a system with motions or motion that repeats in cycles. So a pendulum is an example of this. The mass on a spring that I was talking about. Oh, I forgot about a rubber band. If you take a rubber band and snap it, it'll go boing, boing, boing. What else does that? Can anybody think of any other examples? How about a guitar string? A guitar string does that. There's a very well-known part of physics called string theory, where they think everything in the universe is created by packets of energy that oscillate, that vibrate, like little strings, like a guitar string. really cool. And so for the oscillator, an oscillator is anything that does this. So I start here, swing over this way. I start here, swing over this way, swing back and forth, back and forth, back and forth. That's an oscillation. Okay. Now, same thing here. I have the spring. When the gravity pulls the weight down, it goes down this way, and the spring pulls it back up, and so it just kind of goes back and forth, back and forth, back and forth. If I pull a string or a rubber band, anything really real tight, it could even be a steel cable. But if I pull it real tight and I pull it this way, it'll snap back and forth like this. So that's how guitars work. When it snaps back and forth like this, it creates a sound. You hear sound. Sound waves are actually frequencies. You hear my voice. The tone of my voice is the way that my vocal cords vibrate back and forth, not unsimilar to this. So my vocal cords vibrate back and forth like this thing over here. That's the frequency. So some people have a very deep voice, their vocal cords don't vibrate as much. Somebody with a really high voice, their vocal cords vibrate really fast. Okay, they have a higher frequency. And those of you guys in band, some of the instruments have a lower vibration, which is a lower frequency, and then some of the instruments have a higher frequency. It's just based on how often they repeat the cycles in a second. Okay, and that's how things like circle of fifths work. That's actually a mathematical thing. It has a lot to do with the frequency, believe it or not. Anyways, can I move on to the next slide? So when you look at this, one complete cycle, you don't have to write anything down, just look at it. If I let go here, all the way here, and all the way back is one cycle. Or if I start over here, if I start right here, all the way over here, and all the way back is one cycle. And then you have to time how long that takes with a stopwatch or something, right? So one full cycle is one complete back and forth motion. The period is the time that it takes. You don't need to write this down because we wrote it down on the other slide. And it says the period T is measured in seconds. We wrote all this down on the other slide. I got excited, started teaching everything. But that's what they're saying. If I said hit the stopwatch, stop the stopwatch, whatever that time is, that's the period. Okay. Now let's play a game. What is the period following the oscillations? Earth rotation. So the Earth is here, it rotates around in a full circle. If you were to guess, what do you think that period is? Yes. 24 hours? Yep, one day. Or 86,400 seconds. Yeah, one day. What about your heartbeat? Doodle. Yeah. Take a guess. What's an average heart rate? Anybody know? Okay, so what would that be per minute? That'd be like a little bit more than one per second. So it's about 1 second. Hand on a minute clock, 1 hour, or the minute hand. right? So the minute hand, it takes 1 full hour for it to go around the clock. A classroom pendulum, I don't have one. You guys broke it. Not you guys, but people broke it. Typically 1 to 2 seconds, depending on how long the string is. All right, so I do want you to write this down. Frequency is how many cycles are completed in 1 second. The frequency is measured in hertz. So it's how many cycles per 1 second. So earlier, I wrote down the example from I said that the time it took for that oscillation of the pendulum was 7 seconds, right? So we had, whoops, wrong color. We had the period for the pendulum was 7 seconds. Now to find the frequency, we said that was 1 in 7 seconds. But really, to convert it to hertz, I need to make this 1 second. So the easiest way to do that is just to put it on a calculator and get a decimal. So I really need to just say 1 divided by 7. And so that decimal, 0.14, whoops. So my frequency then would be 0.14 hertz. Because that's how fast it would take to do 1 cycle. Now that's a unique situation. Most things that we measure frequency on, it has multiple cycles per second. Okay. Does everybody have that written down? So what frequency or how many cycles are completed in 1 second? Your heartbeat. Well, we said 1 to 2, right? Oops, I hit the wrong button. So 1 to 2 beats per second, or 1 to 2 hertz. A fan that rotates 360 times in a minute, 6 cycles per second, or 6 hertz. The vibration of a guitar string is about 100 to 800 hertz, depending on the note. So when there are octaves in music or chords, they work because the frequencies, there's a mathematical relationship. I don't want to get sidetracked with it, but look it up sometime if you're curious, or we can talk about it after the notes. But harmonies are really based on the frequencies. There's a mathematical relationship between the hertz. And I didn't know if you know this, the reason they're called harmonies is because they're oscillations. They're harmonic oscillations. That's what makes the sound. Okay, does everybody have this written down? Okay. So you don't need to write this down again. You already wrote it down. So just to kind of recap, remember that this T is the period which is mathematically equal to 1 over the frequency, and vice versa. The frequency is 1 over the period. So they're reciprocals of each other. Now, the only thing with the frequency, and you might want to write this down somewhere, is that wow, to make it hertz, somewhere just write this down, hertz has to have the number 1 in the denominator. Uh-oh. I need spell check for my PowerPoint. No suggestions. Straight off the dome. All right, so hertz has to have 1 in the denominator. So you have to divide top by the bottom. That'll give you 1 in the denominator every time. So if you look back here, Mr. Adams plugged this in the calculator. I set 1 divided by 7, and that gave me this. Okay. Does everybody have that written down? This was bottom. It's running out of space. It's not easy to write with one of these things, because I can't see what I'm writing on the paper. I have to look at the screen, and then I run out of space. All right. You don't need to write this down. I just kind of really want you to look at it. So oscillators occur in systems with stable equilibrium. Potential energy increases from the equilibrium. So right here at this point here, you have the highest potential energy. Down here, you have the lowest potential energy because it's mostly converted to kinetic energy. Up here, you have the highest potential energy. Now, there's some sort of restoring force. Actually, sketch this image out because it is important. So just go ahead and draw this picture in your notes somewhere. Now, these restoring forces, that could be a spring. It could be gravity. Or momentum. There's other types of restoring forces. Just think of any force that pulls things, right? So there's electromagnetic force that could pull or push things away. But usually the restoring force is a pull. So the spring will pull it back up. Gravity will pull it down. The spring will pull it up. I just realized I misspelled the word spring. It's been a long week for Mr. Adams. I had to adjust to the weather. Okay. So when it's up here, either gravity pulls it down and creates that momentum, and then when it gets here, gravity pulls it down again. Now, in the case of something that's connected to the spring, gravity pulls it down, the spring pulls it up. Now, on a guitar string, it's momentum, because when you pull it this way, you let go, it snaps back. So it's actually the actual string itself. It's either the guitar string or a rubber band or whatever that has some sort of elasticity that snaps it back and forth. So that restoring force creates like a stable equilibrium, right? Now, what happens in most cases is that there's some sort of friction, or usually it's like friction or yeah, it's mostly friction that slows it down, right? The guitar string that goes, the note ends eventually because the string is kind of tight, right? So it wants to go back to its natural state. It doesn't want to keep bouncing back and forth. It is hitting air and experiencing air friction. But I think the tightness of the string or cable or whatever it is that oscillates will slow it down. In the case of a pendulum, gravity, it hits air as it swings through the air. That slows it down. And gravity wants to pull it towards the center of the earth, so gravity kind of pulls it down towards the center. Anything with a spring, the spring, again, whatever the object is connected to the spring is going to hit air, and that'll slow it down a little bit. So eventually the potential energy and the kinetic energy gets used up. There's other things too. So what provides a restoring force in a simple pendulum? Or what provides it in a spring? Well, the force of gravity, the spring force. Gravity has an impact on this too, but the restoring force is what pulls it back. What pulls it back, right? Gravity. So think of it like this. I add work to the system because I lift the ball. I misspelled the word lift. That's interesting. So that puts work in to the system, and that makes it have potential energy. Okay, but the force of gravity creates this motion. And then momentum from this point on carries it this way. But gravity pulls it back in. So the restoring force on this one is gravity. Now this one, gravity does the work, adds the work to the system. But the spring force, because it has a constant, it wants to go back to its natural state, will pull it back up. So that's the restoring force. Okay. Give you guys a second to write that down. This does not look like an arrow. All right, can I move on to the next slide? Okay, so let's look at some data points. I'm just going to turn my face off. I'm tired of moving it. It says, is there a pattern? Well, the easiest way to tell if there's a pattern is to graph this. So if I graph this, I get something like this. Do you guys see a pattern there? No. I do, though. You want to know what I see? I see it goes from 8 to 16. I see that right here at 12, there's nothing. I see that it goes up. What's the difference between 16 and 12? 16 minus 12 equals 4. Now, if I go right here and do the same thing, right, I've got 12 minus 8, which also equals 4. Here's an interesting thing. This low point here to this low point here, this is 7 seconds. So from here to here is 9 seconds. A pattern repeats, sort of, maybe. So maybe it has a period of 16, and it looks a little off, but 16 minus 7. Maybe the period's close to 9 seconds. So maybe there's a pattern, something similar to this. Let's see if we could do that. So if I come up here, maybe I come in here somewhere, but let's start here. I come down, around. Does that kind of look like a pattern? Yeah. Now, if I collected the data and it looked like that, and I wasn't sure, and I couldn't obviously see the pattern, what could I do differently? What would make it easier for me to determine the pattern? Anybody have any guesses? Well, I notice that I'm taking a snapshot like every 2 seconds. So I take a picture here, I collect data here, I collect data here, I collect data here. It's about 2 seconds apart, right? Would it be easier to recognize the pattern if I had data here and here and here and here? If I had more dots? Yeah, it'd be a lot easier to see the pattern. So I could change the increment in which I collect the data. Now the amplitude is 4 meters. How do I know it's 4 meters? Because we're measuring the position in meters. As I said before, from here to here is 4. From here to here is also 4. So that's the amplitude. The time from peak to peak is 9 seconds. So that's the period. Now the frequency, and let me show you how you calculate this. Remember that T equals 1 over F, and then if you do a little bit of algebra, we get that the frequency is equal to 1 over T, which is equal to 1 over 9 seconds. Then anybody remember how I figure out the hertz? What do I do with the top number and the bottom number? Yeah, I just got to divide it. So I'm going to pull this up, and I just say 1 divided by 9. I get 0.1 repeating. So there's that. So then my frequency is equal to 0.11 hertz. That's where that comes from. Well, what they did that was really clever, we just said it has to be cycles per 1 second. So we did the math to calculate what it is, but what they did is they just looked at 1 second. Now, it's really hard to determine how much of the cycle was completed. So they're saying this was completed here, and then this is another part of the cycle, and this is another part of the cycle, and this is another part of the cycle. So every 1 second, so they divide that up. Okay? Does everybody have this written down? All right. So let's determine the amplitude, period, and frequency of this. So sketch out this graph roughly. And I'm going to do these in different colors. So purple will be our amplitude. So to determine the amplitude, you just got to go from peak to valley. So there's a midway point right here. This is midway between 5 and 10 is 7.5. Oh, darn you. And then you have negative 7.5 down here. So I believe the amplitude, did they use a capital A? Some textbooks use a capital A, some of them use a lowercase. So I'm just going to do capital A. I think that's what they use. Is 7.5. Now the period, remember, is the time that it takes for a cycle. So it doesn't matter where we start. If I start here, it makes it a little easier. It looks like it takes 8 seconds. So T is equal to 8 seconds. This is frustrating. I don't like how that looks. Oh, wait, I said I was going to do different colors, didn't I? Now let me use red. So we start here at the bottom. Here at the bottom, it's 8 seconds. So the period or time it takes to complete one full cycle is 8 seconds. Now the frequency we could calculate mathematically. Whoops. We'll do that in blue. Remember that the frequency is equal to 1 over T, or 1 over 8. And if you do that on a calculator, isn't that 1.25? Or 0.125, I'm sorry, I said that wrong. So that's 0.125 hertz. This is equal to 0.125. So I think those are my answers, right? Okay, let's see if we're right. Ready? Does everybody have this written down? Well, my amplitude is definitely 0.75. Oh, we forgot to write the units. It's measured in centimeters, so make sure you write down centimeters. It takes 8 seconds to go from one peak to peak or valley to valley. We use valley to valley. They're using peak to peak. And they rounded it to 0.12. Technically, it's 125, but they're using significant digits, I think. Are there any questions so far? All right. So if an object, this I need you guys to write down. We'll do this together. It says the frequency is 50 hertz. So let's do this one. It says the frequency equals 50 hertz. What's the period? Well, the period is 1 over the frequency. Right? Because remember that the frequency is equal to 1 over t. And if you do a little algebra, you multiply both sides by t and divide both sides by f, you get is 1 over the frequency. T is in seconds, F is in hertz. Okay? You guys have that written down? Drum roll. Yep. Oh, wait. Oh, they wanted us to convert it. So 1 over 50, yeah, write down 0.02. They wanted us to convert it into a decimal. We were right. I guess you got to divide the top by the bottom for the seconds, too. Let's do this next one. It says the mass of a spring moves from one extreme of its motion to the other once every second. What is the frequency? Well, the time of the period is 1 second. So the frequency is equal to 1 over 1 second. Wait. One extreme of its motion to the other. Oh, this is a little tricky. So it says that a spring mass moves from one extreme of its motion to the other once every second. So let's draw it out. I've got this little thing here. It moves from this extreme all the way down to the extended one on the bottom. This is like, and this is the compressed one. That happens in 1 second. Is that one full cycle? No, it has to come back. So it's technically 2 seconds. Woo, almost got that one wrong. So it's technically 2. So then over here I have 2 seconds. 1 divided by 2 is 0.5, right? I looked at all the answers. I said, none of the answers are 1 hertz. And I said, well, what am I missing? All right, let's double check that one. Does everybody have everything written down? Yeah, the period is 2 seconds because it takes 1 second to go down and 1 second to go up. That's it. All right, give me a second.